Welcome to the deep dive. Okay, so you've been hitting the books, wading through terrestrial magnetism, and now we're here, we're going to cut through all that dense physics.
Yeah, pull out the really important bits.
Exactly, the nuggets you actually need, shaped specifically so you can nail those ATPL theory questions. This whole deep dive, it's laser focused on making the Earth's magnetic field make sense for the exam.
And look, this stuff, it's absolutely foundational. The source materials we're drawing from, those technical manuals on nav and magnetism, they're not just exam fodder. Not really.
No, it's more than that.
It's about understanding, the most basic direction finder you've got in the cockpit, the magnetic compass. If you get why it behaves the way it does, you understand its limits, its weaknesses.
Right. So our mission today, let's call it precision. We need to really get our heads around why the compass does what it does, especially the errors.
Ah, yes, the errors, deviation and variation.
We need to break down what causes them. So that means understanding the difference between the aircraft's own magnetic field, its deviation, and the Earth's sort of natural geometric wonkiness variation.
Two very different beasts.
Okay, let's start at the beginning. The absolute basic building block, the magnet itself. So magnetism, it's ancient, right? First noticed in magnetite, that natural iron oxide. But for our purposes, the definition is pretty straightforward.
It's just that property, isn't it? The ability to attract iron. And crucially for us, the way it tries to point north when it's free to move.
Yeah.
Like a basic compass.
And these days, obviously, we're not using rocks.
No. We manufacture magnets from metals, alloys, mostly iron and steel, the ferrous stuff.
Yeah.
And it's how these materials can become magnetic, sometimes forever, sometimes just for a bit. Well, that's the root cause of deviation later on. #, defining the basics. The magnet and the field.
Okay, so you've got a magnet. Around it, there's this invisible area of influence. That's the magnetic field.
Right. And we often picture it with those lines of force. You know the experiment, iron filings on a card.
Yeah, classic physics demo. They trace out the pattern, showing how the lines flow, and they really bunch up near the ends.
And those ends, those areas where the influence is strongest, those are the poles of a magnet. Seems simple, but this leads to a really critical rule, one that pops up in exams.
Which is?
Every single magnet has two poles, always, without exception.
Ah, right. This is the point that gets hammered home in the textbooks, isn't it? Because it tells you something fundamental about magnetism. You cannot have a unit pole. A single pole just doesn't exist.
Exactly. Take a strong bar magnet, saw it right in half. What happens?
Instantly, you get two complete magnets. Each half grows a new opposite pole right where you made the cut.
You just can't isolate a north or a south pole. It shows that magnetism isn't just stuck at the ends, it's like woven into the entire structure of the material, down at the molecular level even.
Okay, let's get the terminology straight for navigation. You hang a magnet so it can swing freely. It lines up north-south. The end pointing north, we call that the north-seeking pole.
Or the red pole, that's the common convention.
And the other end pointing south.
That's the south-seeking pole, or the blue pole, red and blue.
Now, here's a detail that can trip people up, but it's crucial for ATPL clarity. If the red pole is seeking north, it must be attracted to something in the north. And we know, unlike poles attract, so does that mean the Earth's magnetic pole up in the Arctic is actually a blue pole, a magnetic south?
Precisely. That's exactly right. Our naming convention, red for north-seeking, is based on the direction it points, not its actual physical polarity relative to the Earth's field. The Earth's geographic North Pole is near the Earth's magnetic South Pole. It's a bit confusing, but vital.
Okay, that makes sense. Convention based on seeking. Now, the field direction itself, those lines of force we talked about.
Yeah, the convention is they flow out from the red pole and loop around, going back into the blue pole. That defines how fields interact.
Which brings us back to the simplest rule of all, interaction.
Like poles repel, unlike poles attract. Red repels red, blue repels blue.
But red attracts blue.
Always. That simple rule governs everything, from why your compass points north-ish to why the metal in your aircraft frame can pull the compass.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best